Chapter 8, Covalent Bonding. Section 8.1, Molecular Compounds. Here's our objectives. Distinguish between the melting points and boiling points of molecular compounds and ionic compounds, and describe the information provided by a molecular formula. So those are the things we're going to cover in this section. Okay, first let's talk about molecules and molecular compounds. And not everything exists as molecular compounds or ionic compounds. Some things exist as noble or as elements, like the noble gases. Those do not form compounds, they're just atoms, and that's how you would find them. Some, like I said, will exist as ionic compounds. That's what we talked about in the last chapter. And then the ones that we're going to talk about in this chapter will be molecular compounds, ones that share electrons versus transfer electrons like in ionic compounds. So if we have elements like, or compounds like water, HCl, which is hydrochloric acid, these have very different properties, even though they're similar, in formula, but property-wise very, very different. So, you have water, which is H2O, and you have HCl, and so they're, they both have hydrogen in them. They have another, a very electronegative atom, yet quite a bit different in properties. Water, the properties of water. Hydrochloric acid, definitely wouldn't want to be drinking that. So definitely some different properties there. Well, in both of these, though, the atom is held together by shared electrons. Electrons are shared between two different atoms, and that's a covalent bond. So make sure you understand that word. Covalent bond means that we're sharing electrons. If we create these shared electron groups, we call those molecules, and they are, once again, neutral. Just like in an ionic compound, we said they were neutral. Molecular compounds are neutral also. The difference being, in ionic compounds, an electron was exchanged. An electron was given from one atom to another. Molecular compound or covalent compound, these atoms these electrons are shared. Now here's a term that you do need to be familiar with, because we're going to use this a lot. There's going to be some things we'll talk about down the road. So diatomic simply means a molecule that has two atoms in it. So if our example of HCl, that was a diatomic molecule. It has a hydrogen, it has a chlorine. That's a diatomic molecule. But even things like oxygen doesn't exist like this. It exists with another oxygen atom, so it exists as O2, and that's a diatomic molecule. Two atoms sharing electrons. So if we have a compound that's made up of these molecules, we call that a molecular compound. Molecular compounds tend to have low melting points, low boiling points. Ionic ones, we talked about how they had very, very high melting points, like salt was 800 degrees. Molecular compounds, very low. Usually, these things are going to be gases or liquids at room temperature. So, water, molecular compounds, a liquid at room temperature. Oxygen, nitrogen, those are gases at room temperature. Those are molecular compounds. Typically, these compounds tend to be gases and liquids at room temperature. Most of these are composed of two or more nonmetals. So maybe hydrogen and oxygen like water, or hydrogen and chlorine like hydrochloric acid. But they're usually nonmetals. You don't usually have a metal involved when we have a molecular compound. So let's talk about molecular formulas. And when we have a formula, it tells us the ratio of the atoms in a molecular compound. It shows us how many of each atom there are in each compound. For instance, you could have CH4, which says that there's one carbon. If there's nothing written, it's a 1. 1 carbon, 4 hydrogens. Or you might have NH3, 1 nitrogen, 3 hydrogens. Or maybe you have C6H12O6, 6 carbons, 12 hydrogens, 6 oxygens. All of those are examples of molecules. And what you need to be familiar with is what they mean, what the numbers tell you. And obviously the numbers are going to tell you how many of that particular atom exist in that molecule. So the molecular formula tells you the actual number of atoms, not just the lowest whole number ratio. In other words, when we talked about an ionic compound like salt, we said it was NaCl. That's simply a ratio. It's 1 to 1. But, if you look at the crystal, you can't tell which sodium goes with which chlorine and so on. On the other hand, if we're talking about something like H2O, that's because that is a particular molecule. There's a hydrogen molecule bonded to an oxygen molecule and another hydrogen molecule there, and you get this molecule that acts independently from all the other molecules of water. And the other thing is they don't have to be in whole number ratios. For instance, you could have hydrogen peroxide, which is H2O2. Now that's not the lowest whole number ratio, and certainly HO is the same ratio, but since this molecule exists as 2 hydrogens and 2 oxygens, that's what we write for the formula. And here's just a couple of different ways. So we're talking about NH3, and here's a couple of different ways that you'll see this drawn. Obviously, this is kind of a popular one in books because they can draw those kind of things. We will get to later on make some molecules with ball and stick models, and they'll look very similar to that, so that's a pretty typical way of doing it. This is kind of another way that I've seen in some textbooks. It's probably not as common as some of the other ones. And then this is kind of the way that we'll write most of our things, in just structural formulas of them given like that, so that's pretty typical in there. Alright, so that is the end of section 8.1.